Home automation is convenient and justifiably popular. But what if I told you you can do the same thing outside in your yard, with convenient watering, feeding of pets, hydrating of pets, camera surveillance, all off the grid from the convenience of your device from anywhere in the world. This is a project that I've been working on for months now, designing, prototyping, building, and troubleshooting. The final product has literally transformed our lives, so I'm very excited to share it with you. I can't cover every little thing step by step in this video, so instead we're going to go over the key features and the lessons I learned implementing them. You might remember in the past I made a video about moving house and then setting up the backyard for these guys. These are our miniature goats, Brett and Jermaine. And in that video, I created some play equipment to keep them occupied. And as you might expect, they have progressed, growing quite a bit, big enough to jump up onto the roof of their house and turn it into a jousting arena. They've probably grown so much from all the food they've eaten, including the bark off these two large trees. When we first got them, they were small enough that they needed to be bottle fed 3 times a day. And as we weaned them off this milk, a noisy problem emerged. Imagine this noise ongoing, except them standing on the middle of their play equipment, bleeding for us to feed them, somewhere between 5 and 5:30 AM every day. To say we hated this was an understatement, and our neighbours certainly didn't deserve to be woken up like this either. However, this project did manage to solve the problem entirely with the following features. If you're building along at home, you might not need all of these features, but here's what the system can do. Firstly, it connects to Wi-Fi, so I can control it anywhere in the world where I have internet. No special software is required, all I need is a web browser on my laptop or phone. This whole system is completely off the grid, with a battery built in and a solar panel for charging. This system offers control of multiple water sprinklers. Most people would likely want this for watering plants, but goats hate getting wet, and it's amazing how effectively you can herd them just by using sprinklers at the right time. This project allows me to provide food and water for pets without leaving the house. And for me, this was the game changer, as setting up an automated feeder completely eliminated the early morning bleeding. This system has multiple cameras for monitoring and/or recording, and this is essential to be able to check on food and water levels, which means the pets are looked after even if we're not around. And finally, any of these functions can be scheduled so they happen automatically each day. Ideal for keeping things going if you're at work, asleep in bed, or if you're going to be away from home for a while. We'll work our way through the key aspects, starting with the brain. This is an Arduino Uno, a programmable microcontroller that's perfect for this application, particularly with a Wi-Fi shield. And this is an ESP8266, which works in a very similar way. We can actually get these Wi-Fi modules separately to use, for instance, with a 3D printer. But this Node MCU board is the equivalent of an Uno plus the Wi-Fi module already together, complete with antenna and spare input-output pins. Maybe the best thing is how cheap they are. We're talking $8 for a board that's ready to go. I actually had a few of these boards sitting around for a while and hadn't used them because of some misconceptions. Basically, I thought I'd have to learn a new programming language software package and I'd have to muck around to create a web page. But the reality is that these boards are supported by Arduino, they're very popular, with libraries and tutorials available, and serving a web page is done from the same Arduino sketch. So let's get it set up. The first thing we'll do is come to the GitHub for ESP8266 Arduino, and then we're going to scroll down until we get to the section Installing with Boards Manager. There's a URL for us to copy, and then in Arduino we're going to come to File, Preferences, and under Additional Board Manager URLs, we're going to paste it in and hit OK. We'll then come up to Tools, Board, Boards Manager, search for ESP8266, it should be the top result, and you can click to install it, which I've already done. You can then come to Tools and change your board, and there's many to pick from for ESP8266, but if you're following along with the exact one that I've linked, we want this one, Node MCU 1.0 ESP12E module. One page I found particularly handy was this pinout reference from Random Nerd Tutorials. This page has a section for our exact development board, and it will confirm the pinouts, but more importantly, There's a table that tells us which pins we should avoid and which ones are safe to use. For instance, there's some warnings here about boot failing, and I found that's exactly what happened to me if I had a relay connected to certain pins as the board was powered up. Therefore, this page was an invaluable reference. One more thing that's different to other Arduino boards is that when we specify pins, we need to say D5 instead of just 5 to select the correct ones. If you have experience with these boards, you might want to write everything from scratch. But if, like me, you're new to them, I'd recommend finding a tutorial with some example code to work through. Shout out to Rui Santos from Random Nerd Tutorials once more. For most examples you'll find, you'll need to install your Wi-Fi details before you upload the sketch. After that, you can select your port and upload just like any other Arduino board. Once we're done, we can come to Tools and then Serial Monitor, where the ESP board will tell you which IP address it's connected to your local network. Enter this in the browser and start to experiment. I'd recommend looking through the code, seeing where the pins are set up, the sections where the Wi-Fi connects, and then where the web page encoding begins. We have a function set up to handle the two outputs being turned on or off, and then we have our actual web page following that. In this example, delivered one line at a time using client print line. I modified and expanded on this first example, which worked great until I added a webcam. More on that later. The problem being that every time I toggled a button, the whole page would reload and the webcam was slow to embed. So I went Googling once again and found this Donsky Tech tutorial on setting up an AJAX page, which means that the connection is asynchronous. In essence, I could send and receive commands without the whole web page reloading. The structure was a little different, but once again I was able to add and expand until I had the final version of my page. As you can see, I can click to operate the functions without the page reloading, and I can send requests to update the voltage or the status in much the same way. So thanks to Random Nerd Tutorial, Donsky Tech and others, you should be able to find a starting point to save you a lot of time. I mentioned earlier that I can access the system from anywhere in the world with internet, and to do that, I followed this guide on setting up OpenVPN natively on my TP-Link router. Most popular router brands will have similar functionality. This project was ongoing over many weeks for me, and as such, every time I needed to update the code with a new feature or perhaps a bug fix, it wasn't convenient for me to go outside, unplug everything, and bring it in to plug it into a computer. Fortunately, I didn't need to because there's a much better way. If we come up to File, Examples, for our Node MCU board, we have a sketch called Basic OTA, or Over the Air. In essence, this allows us to update our firmware wirelessly over the Wi-Fi network. You can add the important parts of this to any other sketch, including the library at the top, copying and pasting all of these commands into the setup section, and this single line into the loop. And that's exactly what I did when developing my sketch. After uploading via USB the first time, you'll notice that under ports you should have a network port, which you can now select. And from now on, you can update your sketch over the air without having to go outside and collect any of the hardware. Unfortunately, there is a bug where sometimes this uploading dialog box doesn't disappear and you have to restart Arduino IDE. But even so, it's much more convenient this way. So starting with the Donsky Tech tutorial, I've added things like OTA and expanded until the sketch met my needs. If you'd like to use it, it's linked in the description below. I've added a lot of comments to my sketch explaining it as thoroughly as I can, and hopefully that helps. But for now, we're going to turn our attention to the hardware. Here is my completed electronics, and honestly, it's a bit of a mess. And that's because I kept on adding to it as problems came up and as I wanted to add new features. For instance here, adding a MOSFET to only switch one of the cameras on when needed to preserve battery life. As you can see, I used prototyping board instead of making a custom PCB. And if I was to remake everything from scratch now, a custom PCB is what I'd do, as it would be a lot neater. This current approach might be ugly, but it is entirely functional. Let's try and explain this without a proper schematic. The blue terminal in the upper left is where 12 volts and ground come in. And on the underside of the board, I have a 12 volt and ground rail. From here, ground is sent to one pin of all of the green output plugs, and 12 volts is sent to one pin of all of the relays, with the other pin of the relays being sent to the green output plugs. That means each green output supplies ground as well as a switch 12 volts through the relay. Connected to the 12 volt supply is a 5 volt voltage regulator. Therefore 12 volts goes in and 5 volts comes out to its own rail. That 5 volts then goes through to power the logic side of the relays, as well as the ESP8266 controller. As you might expect, the controller also has output wires that go through the perf board and to each of the relay modules. There were some other components added later on, such as a camera to monitor the feeding was going as planned, except this was drawing far too much power, so I added a MOSFET so I could switch it on only when required. These IP cams can consume a surprising amount of power, especially during the night when they use an array of infrared LEDs to light up their immediate area, so being able to turn them off whenever they're not needed is a huge plus. This MCU can read analog voltages up to 1 volt, and thanks to a voltage divider up to 3.3 volts on this board. So if we add an additional 1.2 mega ohm resistor to the analog voltage input, we can safely measure somewhere up to around 14 volts, which allows me to comfortably measure the state of the battery without any additional hardware other than this resistor. Another thing I added later on was a cooling fan for the VREG, which was browning out on hot days. But the fan was also remaining on cool days when there was less solar and it wasn't required. So I turned to a solution designed by Chuck from Filament Friday that I milled at home in a previous video. It uses a thermistor wedged against the VREG and a voltage divider circuit to only allow power through to the fan once the temperature exceeds a certain level. Another change to aid efficiency and allow the battery to last longer on cold and rainy days. Whatever your setup, I would recommend getting it mostly working on the bench before you move to the next step, and that is selecting an enclosure, a battery and a solar charging system. It's really important to know how much power your system will use when idle, as well as how much it will go up when certain components are turned on. For instance, my system uses 87 milliamps when idle, and just triggering a relay with nothing connected to it raises that to 155. Once you have an idea of consumption, you can then select a battery. With this 12 volt sealed lead acid battery, the one I ended up going with. With 12 amp hour capacity, it means my system can sit idle for well over 5 days. However, in real life, the time period will be shorter because I'm turning on and off motors and sprinklers. With the battery and electronic sizes known, I could then pick an enclosure, with this enclosure being waterproof, robust, and large enough. I designed some printed parts to hold the components inside, and then I drilled and tapped holes to hold the printed parts to the base plate that came with the enclosure. Next up, a 12 volt solar panel, with my final one being 20 watts. I paired it with this cheap miniature PWM solar charge controller, programmed to work with lead acid batteries. I bolted it inside the enclosure and it's really simple to use. There's inputs for the solar panel and outputs for the battery as well as your load. It's tight, but everything did end up fitting inside the enclosure with some 3D printed mounts for the solar panel on the lid. The whole thing is screwed down to some brackets which are simply screwed to the fence post. Consider going bigger than you think for battery and solar, or you could end up with an underpowered system and having to buy new components just like me. So what do we need to have phone controlled sprinklers? It was all new to me, but there's plenty of irrigation products available. And the first thing you need to do is to select what diameter poly tubing you want to use. There's 3 common sizes available and I went for the middle of the range 19mm. Everything, by using small components and adapters, is modular. Some items have barbs for the hose, others we use a screw-in fitting with plenty of thread tape. We have adapters to go from the garden hose outlet to the poly tube, and then we run the tube around the yard using T-pieces to go up to our sprinklers. The key component that talks to our electronics and turns the water on and off are these solenoids. We can unscrew the actual solenoid from the rest of the assembly and see it in action, and interestingly enough, these solenoids are designed to operate on 24 volts alternating current. And when we use them in their intended state, we can see they draw around 400 milliamps. But our system is powered from a 12 volt direct current battery, not 24 volts AC. If we trigger the solenoids from 12 volts DC, we can see that we draw around 490 milliamps, so a bit more than intended, but from my few months of testing, not enough to make them fail from overheating. We use yet more adapter fittings between the output of the solenoid and the pop-up sprinklers I selected, and then of course we have to run wiring to the solenoids as well. I use this 7-core irrigation cable because it is designed for this job. And to make the connections waterproof, I utilize these grease-filled outdoor connectors which I'd never seen before. They have metal teeth designed to cut through the insulation on wire, and then when you clamp them shut, the grease will fill any cavities. To use them, I removed a portion of the red outer sheathing for the irrigation cable, cut one of the wires and fed either end into the connector, as well as one of the solenoid wires. And there's no need to strip back the insulation from any of these. You can then use some pliers or vice grips to clamp down and make the connection permanent. Repeat for the second solenoid wire and you have a waterproof junction. Now when the ESP module sends power to the relay, 12 volts will go to the solenoid, water will flow through the pop-up sprinkler, and you can water your garden or herd your goats, whatever it is that you need. The next parts are my favorite, automatic animal food and water systems. My first idea for this was to have a feed tube from a compartment with rotating gears on the bottom where the circle lined up once per revolution to allow food through. But then I decided I'd rather have a mechanism where pockets in these outer gears would rotate, and once they were facing downwards the food would fall out. I even got as far as making this completely 3D printed worm gear mechanism, seen here spinning the wrong way, but it was very noisy, had a lot of vibration, and I wasn't that confident in its longevity. So I purchased this geared 36 RPM 12 volt DC motor and designed around that instead. The final design is one of the most complicated items I've ever made, but I'm pleased to say it works flawlessly. It's designed to sit in the bottom of this waterproof container. It won't be waterproof for long because I'll be cutting holes for the food to exit, but because it's designed this way, it's got a robust lid with 6 clips instead of 2. Let's do a quick assembly. We start with a motor mount that screws onto the top, and the original drive gear used a grub screw, but it just couldn't hold the torque. So I switched to this gear that's almost an exact match, and that needs to be pressed on. The end frame pieces have some thin surfaces that need to be drilled out, as this allows them to be printed without support. And once this is done, the motor and motor mount can be bolted to one of the end frames. The end frames are the same, so it doesn't matter which one. Now we prepare the drum, which transports the food, and we have 7 TPU pieces per drum that need to be slid in from the end. The final versions will be tight, but I updated them to be a better fit than what you're seeing here. With all of the seals in place, we can then screw on the drum caps, and there's a notch on the end of each gear that you need to align to ensure the teeth are correctly placed. You should now have 2 assembled food drums where the outer gears mesh nicely. These drums can then be inserted onto the end frame. You'll put a bearing either side of the frame and then a long M5 screw that cuts its own thread as it's inserted. Repeat for the other side and we should be making real progress. If you haven't already, now is the time to solder some wires to the motor as you're about to lose access. The next part is the frame spacer. We feed the wires through the middle and then it simply slides down over the rest of the assembly, constraining the food entry and exit. The second end frame then moves into position, again with a set of bearings above and below before more M5 bolts are inserted. Now is a good time to test if everything is moving freely. If it's rotating the wrong direction, just switch your positive and negative wires. It should also take around 1.5 seconds for each compartment to rotate past. To mount in the box, we start with this template piece, which we position in the middle and then mark with a Sharpie where the mounting holes need to go. When drilling, I would recommend applying minimal pressure, or like me on this first one, you're going to split the container. Don't worry, it can still be used. We now insert some long M5 bolts with large washers at the top to help spread the load through the container and into our printed assembly. And I'd recommend doing the final torquing by hand so you don't break anything. After putting some more M5 bolts on the other side of the frame, you should again test that everything is rotating as it should. If it is, we will proceed. You'll need to cut a hole in one side, large enough for the food to exit, but not so large that rodents can get in. The top cover was developed with a series of laser cut cardboard prototypes, with the 5th iteration being a nice seal. It simply bolts to the top, and then we have 2 TPU sealing pieces that slide in from the end. There's 2 holes in the underside of this piece to mount an optional buzzer, which you'll be hearing shortly. To handle the wiring in and out of the tub, I decided on this Deutsch 6-pin connector. I modelled one half of the plug and took the dimensions of this slide-on retaining clip. A 26mm hole is drilled through the plastic container, and then these 2 parts are bolted to each other from either side. The wires can then be fed through and inserted into the back of the connector with a satisfying click, and then the connector squeezes into the printed parts, where it should again snap into place and be retained very securely. To use the feeder, we simply fill up the empty compartment full of our feed. For us, it's a mix of goat pellets, sunflower seeds and chaff. We give it a big mix, and then the lid goes into position. I added some hooks for it to hang on the wall in their house, and obviously I have wiring that plugs in that goes back to the controller. This was immensely satisfying to see in action for the first time, and the goats have learnt how it works and no longer get their head covered by food. But what about water? Well, this was my first design, and yes, it resembles a toilet. And that's because a toilet is a perfect solution for a self-cleaning drinking system. Here's a cutaway of version 1, and we can see that we have a way to deliver water from around the rim, an S-bend up the top, and compared to a toilet I've made it quite high, so the water level sits near the rim. This one was designed to be printed all in one piece within the bounds of the X1 carbon from Bamboo Lab. For UV resistance, I wanted to print it from ASA and I didn't want any warping. However, I made the mistake of not adding support to these very steep overhangs on the top, and because of this, water could leak through the gaps between the layers. I tried to silicone this, but it was no good. So version 2 was instead a 3-piece design that gave me access to the insides. In a previous video, I had tested Bully Liner and found it ideal for brushing on and making 3D prints watertight, so that's exactly what I did here, building up layers before using Car RTV silicone in between the left and right halves that were then positioned and then tightened down with screws inbuilt into the design. As you can see, as these are tightened, the silicone is spreading nicely. Once that dried, I applied some more waterproof coating, trying to go over the silicone as well as to the outside of the drinker, before I applied yet another round of RTV and connected the lid to the rest of the assembly, again screwing it down and cleaning up any excess silicone. Once this had set, I covered the rest of the exterior in Bully Liner and bolted it into place, connecting up the water as well. The supply is from a solenoid, just like the rest of the sprinklers, and this was the first time that I filled it up with water and was pleased to find that it didn't leak. The water comes up to the top and then drains through the bottom to the height of the S-bend, staying at a suitable level for the goats to drink. This drinker, just like the feeder, can be scheduled on a timer so it flushes and cleans itself multiple times a day. The only thing that's not working is the gravel drainage that I put underneath. Here's a couple of little things that improved the system for me. Firstly, let's talk cameras. And they're not the cheapest, but for my main camera, I'm using a Google Nest outdoor camera. It's mounted and wired to the house, pointing down across the whole backyard. The important thing about these is that you can publicly share a URL, and this URL can be embedded in the web page. It's completely separate to the ESP8266, so if that goes down, you can still access the camera feed from the Google Home app. I also wanted a secondary camera, powered by the outdoor system, to check on feed levels and just to spy on the goats. It wasn't long, however, before the goats found my temporary wiring. And one thing is for certain, they like to explore the world with their teeth. So I redid the wiring, hiding it behind this plastic snap-on conduit. I also switched to this pan and tilt Wi-Fi camera, which has some nice advantages, like being able to check on all the food levels, see which other animals are breaking in and causing mischief, as well as spying on the goats when we can't see them from the veranda. I've also got some nice reactions when I've tuned in to spy on them and make sure that the scheduled feeding is working. It's handy to have a closer audio feed as well. What you heard at the end there was It's Business Time by Flight of the Conchords, which plays every time they get fed. And if you're using My Sketch, there's a section where you can enter your melody in Nokia ringtone format, and there's also a link to the shareware I used to work out the notes for that particular song. Once you have a melody you're happy with, you can play it back to confirm, and then copy and paste the sequence into the sketch so it plays for you. I wasn't joking when I said that this project transformed our lives. The goats bleeding just after 5 AM was extremely stressful, and for a while it looked like we were going to have to sell them. But now, because feeding is automatic, and as far as they can see, has no involvement from us, they have no reason to bleat when they're hungry. If you wanted to reproduce anything from this project yourself, everything you need should be linked in the description. Let me know if you think it's useful or at least entertaining. Thank you so much for watching, and until next time, happy automating your outdoor areas. G'day, it's Michael again. If you like the video, then please click like. If you want to see more content like this in future, click subscribe and make sure you click on the bell to receive every notification. If you really want to support the channel and see exclusive content, become a patron. Visit my Patreon page. See you next time.